Then we come back to the chapter 7, first Brilliant. In fact, when I introduced you the Wigner-Zeit cell, I have actually mentioned this Brilliant zone, right? So we have already learned how to draw the Wigner-Zeit cell in the real lattice. And then the volume for this is equal to that of the primitive parallelepiped. In fact, just the construction, exactly the same way to construct the Brilliant zone, is also adopted in the reciprocal lattice space, and the space so defined is called the first Brilliant zone. That means when we use exactly the same way to draw the Wigner-Zeit cell, but now we are not drawing on the reciprocal real lattice, but we draw on the reciprocal lattice. And for this case, we call it Brilliant zone. Okay, though the physically significance of this Brilliant zone will be appearance in X-ray diffraction and phonon, as well as the band structure. Okay, so it's formed by contracting perpendicular bisector for all the reciprocal vectors radiating from the center of the cell. So I believe you still remember this slide, right? So this slide basically tells us or teach us how to draw the Wigner-Zeit cell. Remember, if this is a real lattice, then this would be the Wigner-Zeit cell. However, all these are the reciprocal lattice, then this would be the Brilliant zone. Okay, so the concept is very simple. When you draw the real lattice using the same way, you will get Wigner-Zeit cell. When you draw on the reciprocal lattice by using the same way, then you will get the Brilliant zone. Okay? So the Brilliant, the scientist, gave another statement of the diffraction condition. He said that you just consider a two-dimensional lattice in the reciprocal space. Then, okay, this, for example, this one, 2D reciprocal space. You just consider that this O as the origin, this point as the origin, this point as the origin. Then we consider a reciprocal lattice vector which connects point O and another reciprocal lattice side. So maybe this one. Okay. Then now you draw a line in the 3 dimension. It will be a plane, but in 2 dimension it's a line. Okay, which is perpendicular to the vector and intersect it at the same in the middle point. So same like the Wigner-Zeit cell at the middle point. You just draw one line perpendicular to the previous line. Okay. Now the X-ray will be diffracted if its wave vector k has a magnitude and direction that is required by the condition 2k dot g equal to g squared, which can be rewritten in the following way: k dot 1/2 g equal to half g squared. Remember this condition in the Bragg law? So we can actually rewrite this equation. We divide by 2. Then you get this one. Okay, k dot product with half g. Then you get half. Okay, actually divide by 4. Because here 2, then here have to be 4. 4 equals to square root of 2. Okay, so you get this one. So it's easy to see that any k vector connecting the origin and the plane will satisfy the diffraction condition. What I mean? It means that from here to here is G, right? Reciprocal lattice. So whenever we connect two reciprocal lattice, the translational vector, the reciprocal translational vector will be G. Then because it's half point, then here is half G and draw one line. Okay. So K dot product with half G, you will get half G squared. So K, you dot product with this half G, you will get half G squared because K is a
其实呢，不管怎么样呢，如
you get
果
it or
你
not?
想见到我的
Okay.
样子，就真的要在
Again.
我身边很久才可以啊。
From here to here is half G, right? And then K
不要走
it
好不
out.
好？
So
你明天就要回北
K
了
dot
你知道
half
吗
G
下面给你
K dot half G, what we get? You get
真的很急。
K cos theta
想要大口大
time
口喂哦。
half G, right? Then K cos theta means you project to this, you project down, then you get K cos theta. K cos theta, you will get this length, which is actually equal to half G. Okay? So K dot half G, you will get half G squared. This one. So K dot half G equal to half G squared. This equation satisfies this Bragg law condition. Okay? So that means that any K that as long as it starts this line but at any direction is fulfill the diffraction condition. Okay, so it's easy to see that any K vector connecting the origin and the plane will satisfy the diffraction condition. That means, okay, here to here, you got K cos theta equal to half G. Even if the K is like this, then this is theta 2. So K cos theta 2, you also will get half G. And then K for this line, for this vector, dot product with half G, you will still get half G squared. You will still fulfill this condition. So that's why it means that any vector that, as long as its origin from this point and then it touches this plane, it will fulfill the diffraction condition. This is the definition given by scientist, a scientist named Brilon, and this is also the reason why in the first chapter we need to connect the center atom to all the nearest neighbor, and then at the middle point we draw one line perpendicular. It is true, remember, because by doing this way we can satisfy the diffraction condition. So in a similar way we can draw other lines in 2D and plane in 3D which satisfy the diffraction condition. The brilliant contraction exhibit all the wave vector K which can be Bragg reflected by the crystal. So the center part of the reciprocal lattice is of special importance in the theory of solids. This is the first Brillouin zone. Okay, the first Brillouin zone is the smallest volume entirely enclosed by the plane that are perpendicular bisector of the reciprocal lattice vector. So in this contraction, this is the rectangle about the origin. Okay, we start from 1D. Okay, 1D lattice, one-dimensional lattice. Brillouin zone is defined as the Wigner-Zeit cell in the reciprocal lattice. Okay, the Wigner-Zeit cell